if we want to start sharing the next bit. So the next segment that we have is an introduction to treeheatr. I don't know if there's a better way to pronounce that, but we're going to find out. So it's an R package to create interpretable decision tree visualizations. And this is a package created by Trang Lee, and she is a postdoctoral fellow with Jason Moore at the Computational Genetics Lab at the University of Pennsylvania. And impressively, she is the author and maintainer of now 5 R packages, and also an active contributor to the automated machine learning tool, Teapot. So thank you, welcome back.
Thanks, Alice. Let me go ahead and share my screen here. Okay, can you guys see? Okay.
Yep, it's looking good. It's full screen now.
Thank you. Right, so I'm Trang. My Twitter handle is Trang1618, and I just posted a link to the slide if you guys want to follow along, but you probably don't have to. Also, on the Google Doc document, I also linked to the package. And so if you would be kind enough, and if you like it, you can give it a star on GitHub if you'd like. So this is treeheatr, and the tagline for this package is that your decision tree may be cool, but what if I tell you you can make it hot? And the idea here is to combine a heat map with your decision tree. And Kavana, I really was hoping that you would cover heat map so that it'll be a smoother transition for hierarchical clustering to decision tree. But just real quick, and I think Karla will talk more about this a little bit too, about decision tree. But essentially, you have a classification or regression problem, and you're going to try to solve it with a decision tree model. But instead of at the leaf node, instead of just saying whether it's true or false or whether a patient is sick or not, now I'm showing the whole data set using a heat map. So that's the idea. Usually, people see heat maps in where the samples or the features are grouped using hierarchical clustering. So you see these dendrograms on the side of the heat map, but in this case, it's really just a decision tree on the side. Okay, so before we move on, I'd like to walk you through a little bit how R is drawing decision trees. And the first is R part plot. You've probably seen this a lot. In each node here, you would see how essentially the samples, how many, like right now we have at the root node, that's 100%. You also have a condition. So if you satisfy the condition, you go to the left. If you don't, you go to the right. And then eventually you arrive at a terminal node for that sample that you're interested in. So in this case, a sample may be male and then maybe older than 10 years old. I think this is the Titanic data set. And they're trying to predict whether a passenger survive or die on the Titanic, and if they have siblings, it seems like they survive. So those are things that you can interpret from the decision trees. Another function is this tree from Viz Network, and this package draws really beautiful tree, but I'm not really sure, how I guess informative or meaningful, interpretable this tree is. So in this case, regressing, I think they're predicting the petal length from the iris dataset on the left here. Partykit plot party is a really, really nice function, and partykit is really what treeheatr is built upon. But for visualization, what they're plotting here is very similarly the node where you have the features, and then it also plots the p-value, so how significant that feature is in predicting your final outcome. And then at the leaf node, it's a little bit hard to see, but they have a label for the prediction, but also how large that node is. So they have n in this case equals to 149, and then they have the error rate. You can also do histogram at the end here of at the leaf node. So in this case, you have let's see, I think the labels are overlapping, and so that's a little bit hard to see, but they have different labels. And so in this case, you know, the first label is most prominent, whereas in this box right here, the second label is most prominent in that box. And the way that you make decision is based on the majority of votes. So what that means is, you know, in each of these boxes, whichever is the most popular label, they label the whole box with that label. So that's just a general, and I think Karla will talk more about this as well. Okay, so built upon PartyKit is something called ggparty, which is even more flexible. So as you can see here at the inner nodes, instead of having just, you know, regular statistics that you see, now you can draw a bar plot, or in this case, density plot. And then at the end, you can even draw a scatter plot for each of these leaf nodes. And my package uses a lot of ggparty structure as well. Just one mention to the Python package, d3viz. They actually put a lot of thoughts into, you know, how to best visualize the symmetries. And as you can see here, we have a stack bar plot on the inner nodes, and at the leaf nodes. This is interesting because not only, so this is a pie chart. Usually pie charts are bad. And I will talk more about this in December as well. But in this case, these pie charts actually show how large these nodes are and how accurate the decisions made in each of these nodes. And so those, I think, are very, very important information. And you know, you can immediately see here what the split does with the labels space. Okay, so this is treeheatr, classifying on everyone's favorite penguins data set nowadays. And so this is different species of penguins that it's trying to classify. And so similarly at the inner nodes, you can see the features and what happens to each of those features if you divide them. There's football length, there's Coleman length, so on and so forth. At the leaf node now, instead of, in addition to the labels, now you have a heat map. So what is this showing here? At each row, we have a feature, and each very thin column that you see here is the penguin. So what are some of the assumptions we can make right away? First of all, you can see that, each of these leaf nodes, you can see how large those nodes are, and where the misclassifications happen. And in general, you can see immediately that the Gen 2 penguins seem to be a little bit bigger, and they live in the Biscoe Island. So that's something that you can draw right away from the heat map. Okay, so how do you use treeheatr? And I'm going to show you in a little bit how easy it is. But just real quick, the core function of treeheatr is called heattree. It actually has an alias that's also called treeheatr, but I find that a little bit confusing. So let's just stick with heattree. And the main argument of heattree can be either a party object. So what that means is that you pre-compute the tree using either PartyKit, like I mentioned earlier, or you can use rpart to compute these trees and then convert it to to a party object using asParty, or a constant party object. I know these words seems a little bit intense, but they really just functions, and this they assign the output is assigned a class. It can be party nodes. So what that means is that you can manually specify the tree, so you don't have to like compute it or anything. You just really draw out, I want, the Biscoe Island to be on the right, and I want flipper length small to be on the left, something like that. So you can draw it and make it into a party node with PartyKit syntax, or it can be a data frame. So the final option essentially is just something that really quick and easy that you can do. So what this does is the package automatically computes the conditional tree for you. And what you would have to do in addition to putting X in the function is telling treeheatr, oh, I want to classify this column called outcome. So that's called target lab. So target label is outcome. And just quickly, some terminology that I kind of decided on this package. I named the target column. I used the word target to mean, you know, the column that has the dependent variable or the outcome or the phenotype in the bioinformatics sphere, and features to mean the predictors or the variables. And so in a lot of the arguments you see like feed colors or like target legend. So those are things that it's associated with. Okay, so I gave this presentation at Our Medicine a little bit a few weeks ago, and so I thought I'd throw in a COVID-19 patient data set. So this is 351 blood samples of patients who were admitted to the Tangxi Hospital in Wuhan, China, and the original paper here, I think published in Nature Medicine, no, I'm sorry, I think it's like Nature Biotechnology. Anyhow, they were able to establish an XGBoost model, and then they used the feature importance from XGBoost to select these 3 features, and then they took these 3 features, which are lactic dehydrogenase or LDH, lymphocyte levels, and the high sensitivity C-reactive proteins or CRP. They built one single tree from these 3 features, and it turned out to perform very, very well on the test data set. So that was very impressive. And so I thought I'd take the data. By the way, the COVID data set's already built in the package. So as you load the package, it's already there and you don't have to do anything about it. So anyhow, going back to the heat tree, so you put in the data frame here, and because it's the data frame, we know that we have to give it a target label. So in this case, it's the outcome. And we have a tree. So in this case, we have, once again, on the rows, we have the features. So in this, we have LDH, CRP, lymphocyte, and also the outcome. And then on the tree here, you can see, you know, lymphocyte seems to be pretty important, but in general, there's a correlation, right, between these 2 variables that you can kind of pick out right away. I'm not, you know, it's hard to literally dig in and see which one it is, but in general, you see like this is a block of high values for LDH and CRP, and so are this ones, and yeah, so I think there's a lot of things that you can infer from here whether a patient survive or die from COVID-19. Just a few more options here. So you can say, oh, I'm not really worried about the features, it's too complicated, I don't want to see it. You can set feed equal NA to just show the tree and the outcome. So if you want to throw this in a lecture where you teaching people decision trees, this is something that you can do. This is a lot of code, but it really just to draw a custom trees, like I mentioned earlier. So this is the party node object, and it's complicated because you have to tell R like, oh, I want first of all this node 1, and then node 2 make that kids of node 1, and so on and so forth. So that's a little bit, it can be a little bit awkward, but in general, it's pretty straightforward. If your tree is simple like this, and then you can put it in and it would draw the tree for you like I wanted to. Yeah, so you can see the cut here is our 41.2 and then 14.7 and 365. It has a vignette, so if you want to explore a little bit more how to change colors of the outcome, how to separate them out a little bit better, putting more information in the inner nodes, removing the whole heat map together, all of that you can do. So yeah, feel free to go there, browse around, and if you have any suggestions or feature requests, feel free to open an issue and I would love to take on the challenge. So this is the end of the presentation. I want to be respectful of everyone's time. I do have a little bit of code to demonstrate, but I don't know how we're doing on time. Alice?
I think
Or is-
maybe best
Oh.
if we just take a question and then we can go to the next bit,
Okay.
unless Karla has other thoughts. Yeah, one question was, I know the presentation is on the graphic or visualization, but is there a way to measure variable importance? It's an important question.
It is a very important question. So no, right now, treeheatr doesn't output any feature importance. Well, okay, I should step back real quick. So in here, if you look into the p-values around here, but this is at each node, where is that? So there is a p-value, and in a way, it tells you how significant that node is in predicting the label. So it can, I guess is the answer. However, how do you aggregate these nodes? Because one feature can spread multiple nodes. And that is when you would have to go back to, if you're really just interested in the variable importance and not worry about like drawing or anything like that, you should go back to the party kit package. And then I'm pretty sure there's a variable importance function there. There is however accuracy or how your model performs. If you actually give it a test data, then it would compute an accuracy and balance accuracy and ROC and so on for you. And you can I used Yardstick to compute these metrics, and so whichever metrics are in the Yardstick package, which if you don't know, it's part of the Tidy Models framework, then you can just like, oh, give me kappa value, for example, then it would print it out for you.
Okay, I think we have a couple questions that are maybe related. So one, everyone is loving it. I think these are really beautiful. But then to try it out on our own data sets, what methods, I guess, did you use to generate the input, like the trees? And a related question, can you directly take in models learned from Carrot or Tidy Models?
Yeah. So it would, right now, if you really want it to be different object, maybe I can try to integrate it in. But right now, all the trees that I take in is of class party. So if you could, let's see, echoing here. Yeah, so if you compute, I believe you said Carrot package. I believe from Carrot if you do decision tree, it does export a tree that you can then convert to a party object by using the as party function. So as dot party, and then you would feed that inside treeheatr. Does that make sense? And if it doesn't work, like, feel free to submit an issue, ping me however you want to.
Okay, I think that answers the question. People can ask you further.
And I can go to the document as well.
Oh, it says yep. Yeah. So, and then if you go and check out my bad answer in the document, you can fix it.
Thanks, Alice.
Awesome. So thank you again. I'm very excited to cluster some penguins or build some decision trees. Yeah. To do this myself. All right. I think this is going to transition us then to our third and final topic. Awesome. So pleased to welcome Karla back to the stage. Karla is one of the co-organizers here at Our Ladies, and she's also the head of algorithm development at Orchestral, where she leads different behavioral data analytics efforts. And so with that, I will pass it to Karla.
Thanks, Alice. So my talk is just going to be a quick intro to random forests. There is a lot to know about random forests, but obviously we don't have a lot of time. And my goal is really to make it an approachable topic for people. So something that's not intimidating and that you can actually try out and use on your data sets. I know there's been a bit of buildup that I'm going to talk about trees. I had not planned to talk about trees too much, other than say that random forests are built upon them. But I can briefly touch upon them as well. So the overview for this set of slides is I'm just going to give a quick background on what forests are, what the random forest algorithm does at a very broad level, some of the advantages and disadvantages of using random forests, and then we're going to go into a basic implementation of using random forests on a data set. And then finally, I want to bring up a few gotchas, which are just important things to keep in mind if you're going to apply this method to your data sets. All right, so beginning with trees versus forests. So forests, as the name implies, is just a collection of different trees. So as you've seen before, and you probably know, a decision tree is one single tree that uses the entire data set to construct the tree, and it uses all the features available. So all the variables that are available are built into the tree or are considered in the tree. Also, with a decision tree, you have the entire, or you have the one tree that makes the determination for a prediction. What random forests do is they are a collection of different trees. So they aggregate across multiple trees, and they use bootstrapped data. So at any tree, you only use a subsample of the data that is available. Additionally, you only use the subset of the features that are available. So you can tune these parameters to get to a better prediction. And then finally, one major difference is that all trees contribute to the prediction as opposed to just having one tree. So this can lead to a more stable model than one tree, where all you have is one data set and everything rests on that one data set to make a prediction. With a random forest, you include some of that variance and variability in the prediction. So the overall algorithm, the general algorithm for random forest, and I stole this from UC Business Analytics guide, so go check it out. They have a really good tutorial there. The basic algorithm here is you take a training set. Actually, important point here, before you use random forest, you should split your data into training and test data. And you want to build your model on the training data only. You want to keep the test set as unseen data so that you can actually test your model on novel data. So given a training data set, you want to select the number of trees to build. This you can specify as a parameter in the model. And then for each of those trees, what you do is you generate a bootstrap sample of the data. So you take a subsample of that data. You grow a regression tree on that subsample of the data. And in that tree, for each split, you select M variables. So you select a subset of variables at random from all the variables that are available to you. You pick the best variable and the best split point among them, and then you split the node into two child nodes. And then you repeat this process until you have reached the stopping criterion for your tree. And then you repeat this process until you've exhausted the entries, the number of trees that you wanted to grow. So overall, this is the main idea behind the random forest. Now, some of the advantages and disadvantages. So the advantages, it's a very popular method. It has fairly good performance pretty much straight out of the box. So you can apply it to your data and most likely you'll get a decent model depending on the data. And it has a built-in validation set, so you don't have to set aside extra validation data in your training set because it's already built into it. And it's fairly robust to outliers. On the negatives, it can be a little bit slow. The larger your data set, the slower it gets. And it's one of the big problems that I find with it. It's not very interpretable. So in business settings, if you have clients that you need to deliver a model to and they want to understand why a prediction was made, it's very hard to pinpoint why that prediction was made. So it's kind of a black box approach in that sense. You've seen Trang's a visualization, and those are really neat. You can easily explain those to your stakeholders and say, well, look, this cut point here makes sense, and then it splits into this. You can easily explain that. With random forests, that becomes a lot more difficult. All right, so going into a basic implementation for how we would use it, and we're going to use a made-up data set. We're going to examine a healthcare data set that looks at the case of the Mondays. So probably you know that there is a condition that goes around where people sometimes on Mondays feel really lousy, they feel tired, they feel frustrated, they don't want to do anything, they just want to crawl under a rock and wait until Friday. So we had a fictitious team of scientists that came up with a way to study this curious behavior that they see in people. So scientists gathered around and decided to survey 1,000 fictitious people, and they assumed that these are the variables that play a role. So they figured, let's include some demographics, so we'll include age. Perhaps the weekly routine, so does the person have a regular job or school that they have to go to, makes a difference. And then they figured, you know, weekend activities, how much fun someone has on a weekend, how much alcohol is consumed may play a role. Similarly, maybe how much someone likes their boss and colleagues plays a role. And then they threw in some health, financial, and social support status variables just out of curiosity. So this is the data set we're working with in the example I'm giving you. So then the researchers turned to us and they want to know, can you build a model that will tell us who will get the case of the Mondays? Okay, so what do we do? So in order to build this model, as I mentioned earlier, we need to first split the data set that we have. So we have 1,000 people, out of which I actually know that 100 have the case of the Mondays. So we will split this data set into training and test. And I chose 2/3 to assign to the training set and 1/3 to assign to the test. I think that's fairly standard practice, but I've seen anywhere from 2/3 to 80-20 split as well. So that's kind of on you. All right, so then the model, I'm just going to present the basic, the very first package that was built for random forests in R. So this is the random forest package here. This is actually built by the author of the algorithm too, so it's the initial one. There are many packages out there currently that handle random forests with different implementations and different variations, just so you know. But we'll focus on the initial one. So before you begin, you want to set a seed for reproducibility. So remember, with random forests, it pulls random samples, and unless you set a seed before you do that random pulling, you're not going to be able to replicate your results. So this will change every time you rerun your code. You're going to get different results. So very important here. All right, so in how you define the model or how you actually run it, a very basic implementation is very simple. So random forest is the call. The formula, you specify your outcome variable. So the case of the Mondays, in this case, this is a 0 and 1 binary variable. And then you say, I just want to throw all the variables in the data set in and see what happens. You tell it where the data is coming from. So our training data set is the data source for this. And we're also giving it the importance equals true flag. And this is because we want to store importance of variables so that we can go back to the scientists and tell them, well, if you just ask these first 5 questions, you're going to get the same results, ideally. Okay, so if we run this code, what we get is an output that looks like this. The first part of the output tells us what model was run, and the number of trees here, the default is 500. The number of variables tried at each split is 3. This is also the default. We didn't give it any parameters here. So what we see here is we get an out-of-bag estimate of error rate, and this is the out-of-bag concept really goes back to the samples that the trees were built on. So remember, when each tree is being built, it bootstraps a subsample from the training data and uses that to build a model and leaves some cases out. Well, those cases are the out-of-bag cases, and then it tests the tree model on that out-of-bag sample and does this again and again and again, and that's where you get your out-of-bag estimate. This value here actually is calculated from the confusion matrix. So if you look at the confusion matrix, you have one side, I always get these mixed up, but I believe horizontal in this case is the true label and vertical is the predicted label. So we have in total 62 cases that have the case of the Mondays, and we have 608 cases that don't have it. And we can see that our model has predicted 601 non-cases correctly, and only 13, unfortunately, of the cases correctly. So, bit of a problem, but let's say for now we're optimistic with our 8.36% error rate. So let's see what other parameters we can tweak in order to improve our model. Same thing, I'm setting a seed here. I'm defining the formula in a more formulaic way. It's the same formula that I've used before. But looking at the parameters here that I can use, I'm giving it dftrain again as the data source. I can specify the number of trees that I wanted to build. I can specify the number of variables that should be sampled at each split. So I give it 2, but this could be 3 or 4 or 5. I can specify the sample size. So the size of the samples to draw. So in this case, it's a percentage. This is a percentage of the training data set. So it can be 50% of the training data set, or it can be 60%. The default is 63%, I think. I can also give it, specify the node size. So I can say what the minimum number of terminal nodes should be for my model. And then again, I'm including importance equals true because I want to store the importance of variables to look at later on. So then these are parameters that I can give it, but how do I know what values to give it? Well, I can use some tuning approaches, and there are many different ways to tune random forest algorithms. Here's one example using Ranger. So with Ranger, you can do a hyperparameter grid search. And what this does is you can specify different values that you want to consider and then create the total number of combinations for them. So in this case, I'm telling the grid that I want to consider trees between 400 and 600 trees. I want to try variables between 2 and 11. 11 is my maximum. That's generally not preferable, but let's go with between 2 and 11. Then we can specify the node size, so the maximum node size, and the sample size. So I can choose different samples to build these training models on. All right, so with these specifications, this leads me to 400 combinations. And what I can do next is go through each of these combinations and compute the model, and then extract the root mean, the error rate. So this takes a while. You may not, there are better ways, especially for the number of trees, there are better ways to do this tuning, but I just wanted to show you an example. So once you do that, you can pull up the top best best models, the parameters that give you the lowest out of bag error rate. So in this case, we end up with 400 number of trees, 8 variables to try, 9 for node size, and 55% of the sample to use. Okay, so let's see how that works. So we run this again, and this looks pretty ugly, but essentially this is just giving each parameter here the top, the hypergrid value from the top row. So it's the same formula otherwise. All right, so we look at our formula here, we look at our output, and we see that our out of bag estimate of error rate has actually decreased. So we have less error in this case. So yay, that improves our model a little bit. And so then now, after we've tuned our model, and let's say we've decided that this is our final model that we want to go with, what we can do, usually we use random forests in 2 ways. So we either use it for predictions, so you can use it for prediction, for classification, or for regression. The prediction part is really simple. So you just say predict, you give it the model, which you saved as an object previously, and then you give it the test set, so you can test how it does on unseen data. You know how it does on your training data set, but you want to see how it does on unseen data. And then you can run the confusion matrix again just to have a look how it performs. In this case, we can see that our model classified 290 people correctly as having non-case of the Mondays, and 13 people correctly as having a case of the Mondays, which is not great because it misclassified a lot more. So another thing that we do, and this has been a question in the last 2 talks here, how do we get variable importance? So you can extract variable importance from random forest. When you run this code here, which gives you a plot of the variable importance, and you can actually extract the values from it as well, but it's easy, it's nice to see as a plot. And this is in the most basic form of it because you can have much nicer and fancier ways of showing this. But there are 2 outputs that you get. So you get accuracy, which the way accuracy scores are obtained is for each variable, it scrambles the values, but maintains the distribution. And then it builds a tree, assesses the accuracy and loss of accuracy as a result of this scrambling. So it picks a variable, messes it up, and then sees how much accuracy is lost as a result of messing up this variable. And then the second output for variable importance is the Gini index. And this one is an index of purity. So the assumption here being that if the variable is useful, it will split mixed label nodes into pure single class nodes. So it will correctly split the cases in such a way that the nodes are pure. For a predictive model, generally you want to go with the accuracy component. So if you want to use this for variable importance, I've seen accuracy being recommended as the way to go. Okay, so now we have a model, we have our predictions, we have our variables, everything's great, right? Well, not quite. So you've probably noticed in my data set, I have imbalanced samples. So I have 900 people who don't have a case of the Mondays and 100 people who have a case of the Mondays. So this is a problem for random forests. So it's very easy with imbalanced samples for a random forest to take the lazy approach and just classify almost everything as the majority class. So in this case, what you would like to do, or one of the options here is to create a balanced data set. So you can do this by, let me see, you can do this by under and oversampling. So you can select a random sample of the people who don't have the case of the Mondays to match the same number as the people who have a case of the Monday. So that would be undersampling. You can oversample. You can also add weights to a random forest model. So if you know what percentage of your population you expect to fall into one class or the other, you can add weights. And you can also try a quantile classifier approach. This is a more modern approach, I believe, and there's a package called Random Forest SRC, which can implement both of these two. So you can try them out and see what works better. As you can see in the output, when you balance your sample, your out-of-bag estimate error rate looks a lot worse than before. But if you look at your confusion matrix, you can see that a majority of your cases are classified correctly as non-cases, and the majority are classified correctly as cases. So this looks a lot better actually when you look at how these were classified. All right, another gotcha that you should pay attention to is, all right, you want to get your variable importance. You want to select the top most important variables that you have. How do you know that those are correct? Well, one easy way to verify and to validate that what you have is a correct list, or at least something that you can trust, is you can include some random variables in your model. So you can make up some variables and call them random var1, random var2, and include them in the model. And ideally, what you'd like to see is that these variables are at the bottom of your importance list here. If they're at the top, you have a problem. So if they're at the top, you can't really trust that your model knows what to do with the random variables, and you can't really trust that the variable importance that you have is accurate. One thing, so a final thing that you should consider, and this kind of ties into the variable importance components. So when you select predictors, when you select variable importance for predictors, when you have correlated predictors, this can be a bit of a problem, at least in interpretation. The decision seems to be a bit split on whether random forest does well or not when it comes to collinear variables. But what happens is it will pick the first variable that it finds, and it will assign it an importance score. And if there's another one that's highly correlated with it, that one is just going to lose importance and going to fall to the bottom. So, or lower down the list anyway. So even though, let's say, work stress and financial status may be highly correlated, because work stress is here at the top and was selected as a top variable, financial status is going to be pushed down. Doesn't mean that it's any less important. So you can't really assign an interpretation to that if you have correlated variables. So just something to keep in mind. What you can do when you have correlated predictors is there are a couple of options. Actually, here are just a few. The internet is full of different options, but conditional inference forests actually perform very well when you do have correlated predictors. So you can access this with PartyKit, and the command here is the cforest. And then there's a newer algorithm that I've come across, which is called Boruta. I don't know how you pronounce it, but it is a wrapper around several methods for variable importance, and random forests is one of them, but this is specifically designed to optimize extracting variable importance. So, with that said, I think this is the end of the talk. So I listed a couple of additional resources. I didn't have a ton of time to add more, but this will be a good start. So that said, thank you very much.
Awesome. Thank you, Karla. Yeah, we have a couple questions. So one would be, since random forest takes so long, did it take a long time to build these slides?
It did not take a long time to build these slides. So Random forest takes a long time on very large data sets. In this case, I had only 1,000 people, 1,000 rows in my data set, so that's not a big problem.
And then another question is the Gini method for variable importance. That only works for tree models, right?
You know, I think so, but maybe Trang can help here.
I think that's correct. Yeah, I think the Gini index is like, it calculates how pure your node is essentially. And so if it's like, yeah, so it's tree based.
And then I think another question which is related to what you already answered on correlated predictors is, do you have any advice about what machine learning methods do work well when you have correlated predictor variables?
I would say try conditional inference forests. I found they work pretty well. I don't have a ton of experience with this Borda algorithm, but I've seen it mentioned many times, so I'm actually very interested in it and want to try it out as well.
Yeah, maybe if anybody has tried it, you can comment, leave your thoughts in the chat. And then I guess another question, which is, will you be sharing your slides?
Yes, they are.
Awesome.
I shared the slides in the
I see them.
Doc. Yep.
I'll paste them.
And I can link the GitHub repo as well, but it's basically the same thing.
Okay, excellent. All right, so it's 7:40, and I think we have time for me to do a little bit of a wrap up and reminder of some announcements. So maybe I will share my slides again, if I can figure out how to do it. Okay. Okay. So thank you for everybody who joined. We had a really great question and answer session, and we'll be posting after the meetup on our site a wrap up of the event, but also we'll be posting any of the slides that have been shared by all the presenters and where you can find the materials. We do maintain kind of a repository of meetup materials on GitHub as well. Reminders of some of the announcements for people who may not have been here at the beginning. Please check out our future events and tell your friends. So finally, I think to wrap it up, if we can do a little virtual round of applause, thanking all our speakers again for coming and volunteering and sharing their time with us. If you would like to join us at a future meetup, please do get in touch. In addition to the ways you can get in touch here, we also have an email address, which is just philly@ourladies.org. Okay, so without further ado, thank you again. Thank you to all our speakers. If you want to keep asking questions in the Q&A, I think that doc will still be open. If we can post it again in the chat before we close the meetup. And then I guess see everybody in October and see you all online as well. Thank you.